Okay, so let's look at some problems using our integrated rate law equation. So here is the first. So I tell you that I have a first order reaction. So we're going to look at a couple of problems today. So in one, I'm going to tell you the order, and in the other, I'm going to give you some data so that we can determine the order. So the information somewhere in the problem will be given to you so that you can determine the order of reaction so that you can narrow down your equations. All right. The second piece of information I give you is the half-life. So for us in A, we are going to have to use the first order half-life equation, and we're going to use that to find the rate constant. So let's write the equation first. So T1 half is equal to 0.693 divided by K. And in this case, I know the time, and we're going to use this to find K. So when I rearrange this, we would take 0.693 and divide it by 20 minutes. And notice that our time is 20.0, so that means that it's not just a counting number, that they've taken some measurement to get that accurate. So both of the values here have 3 sig figs, so my answer is going to have 3. And this is going to be minutes raised to the negative first power. So there's my answer to A. My answer to B, so again, we're going to use first order equation. And in this case, there's no mention of half-life, so it's just talking time. So we're going to have to be using that integrated rate law equation. All right, so let me write the integrated rate law equation for the first order. Okay. Now, it doesn't give me actual numbers here. It just tells me it's 75% complete. So this had to mean that initially I had 100% of A, and we're looking for time. K we just found, so that's my 0.0347 minutes to the negative first. Okay, and then this is negative. And this is equal to the natural log. Now, if it's 75% complete, what goes in this concentration of A is how much is remaining. So if I've used up 75%, there's 25% remaining. All right, so we would, in your calculator, you would take the natural log of 25, subtract the natural log of 100, and then we're going to divide that answer by negative 0.0347. Okay, so I would get, when I subtracted the natural log of 100 from both sides, okay. Then we went T by itself. Okay, so T is going to have units and minutes. And the only thing that really has measured values here is our rate constant. So that determines sig figs. There should be 3. And if I round to 3 sig figs, you should have an answer of 40 minutes. All right, so there's problem number 1. Let's take a look at problem number 2 here. Okay. So I've given you data, and so here's what we see. If I take, okay, I can see that AB is my reactant, and its concentration between the 2 trials here is doubling. And if I look at the rate here, we know that the rate quadruples. Okay. And so this tells me that this reaction is second order. All right, so now I've narrowed down my equations. And so let's look at the question out. I want to determine the half-life, so we're looking at the time for half of it to decay. All right, so the half-life equation for second order is T1 half is equal to 1 over the rate constant times the initial concentration. Okay, so I gave you the initial concentration as 1 molar, but I did not give you the value of K. So we're going to have to figure out the value of K. So rate is equal to K times AB to the second order. So I can pick any of the trials above. So if I use trial number 1, we know what the rate is. And for trial 1, I know what the concentration of B is. I know it's 0.2 molar. And so we divide both sides by 0.2 squared. And so K is going to be equal to 8 times 10 to the negative second. And the units here are liters per mole times seconds. So we can plug that into here. And when I solve for T1 half, you get 12.5 seconds as your answer.